What's up, everyone? Today we're going to solve a pre-calculus level inequality, as you can see on the board, that I will say it almost covers everything that you have learned before you actually take your final exam in pre-calculus course. Except there's no trigonometry stuff in it. So what did it include? Well, obviously it has the inequality part instead of just equation, as well as the exponential function. You can actually think that on the left hand side we have some certain base raised to a power that is in terms of the variables instead of just constant numbers. As well as we have the fraction inside, which is you can think as a rational function up here, because you can see that in the denominator of that fraction, it also contains variables in it. And last but not least, we also have the modulus function. As you can see on the top part of the fraction, we have the absolute value that actually contains the variable inside, so that it's no longer a constant that we can just simply determine it right away and end up with just one result. So, all right, how should we solve it? Here we go. So first, we need to think as the following. Most people will just try to take the log of the base on both sides, which will actually work. But sometimes we need to be worried about what base it is. So in fact, we can, in order not to consider whether we need to change the sign of the inequality, we can actually take the natural log as our base. So what does that mean? It means that we can first put ln on both sides. So on the right hand side, we will just get ln of 9. And why do we not have to worry about the change of the inequality sign in this case? That's because when we are taking the natural log, we need to consider the graph of the function, which is when we are thinking of the exponential function here, when we have a function such as y, or you can call it f of x, which is equal to some certain base b raised to, let's say, just simply the x power. On the graph, we will say that this function looks like going up or increasing if the base b is strictly greater than 1. Then, of course, if we have b is equal to 1, we'll definitely get the function that looks like the straight line, or in fact, it will just be 1 to the x power, which is equal to 1. So of course, we'll actually get the linear function y equals 1, or just a constant function. And if b is lying between 0 and 1, in this case, we actually have the graph of the function going from top to bottom like this, meaning that we're going to have a mirror image to the graph where b is greater than 1. Then, in order to not change the value or not change the sign of the inequality, what we need to do is we need to guarantee ourselves to multiply or divide by a positive value. So when we try to take the natural log on both sides, we know that the natural log is actually the log in base e. In other words, now we're thinking it as we're trying to do both of them in base e and trying to undo the function, meaning that now we can actually set our base b as the natural number e, and in that case we'll see that the function, or the graph of the function of e to the x power is actually increasing. Then as we see that it is always increasing while the x value is increasing, we can just claim that if the left hand side is greater than the right hand side, and we take the natural log on both sides, we can also guarantee that the left hand side is still bigger than right hand side based on the monotonicity of the graph, meaning that it is going in one direction. In this case, it's always going up. All right, so using this idea, we can now continue and actually work on it quickly. So as we take in the natural log on both sides, we can now get the left hand side where the exponent to be the outside here times just the natural log of whatever is remaining. And again, that is just based on the log properties. So one of them says that if we have the exponent or the power, we can just pull it out as products. And on the right hand side, we just have natural log of 9. And of course, we see that 9 and 1/3 has something in common, which is 3. So in fact, we can try to write it as 3 to the second power, or 3 squared. And then on the left hand side, we can also rewrite the 1/3 inside of the natural log as 3 to the -1st power. So again, we can just use the property one more time by bringing out this exponent to the front and this exponent to the front, so that we now get negative the fraction absolute value of x plus 1 all over x minus 2 times the remaining part, which is again ln of 3 is greater than the right hand side, which is 2 times natural log of 3. So again, here comes the reason why we can is in some sense easier to understand by first taking the natural log on both sides and then try to break down the algebra, because now we have ln of 3 in common, and of course we know that ln of 3 is not equal to 0, so we can actually divide by ln of 3 on both sides. Moreover, ln of 3 is actually greater than 1. Well, we see that 3 is bigger than the natural is greater than 1. So in other words, we actually have this as a positive value, and this is also a positive value. So if we know that this is a positive value, we can divide both sides by the same value, and we don't have to switch the sign. And therefore, the natural log of 3 will be cancelled out to leave us this part remaining. Negative absolute value of x plus 1 all over x minus 2 is greater than 2. Okay, so we're gonna bring this up and then move on for our calculation. Okay, in the end of our last board, we actually end up with this step here. So now we just have the rational function inequality here, meaning that now we have to figure out how to deal the denominator. So in class, usually teacher will just ask you to multiply the denominator on both sides, and then we need to try to think of the steps. But again, we can actually use the trick that was actually posted in one of my other videos, which is to multiply the square of the denominator. Why? First of all, we know that if we use an equality sign, we're thinking of the real numbers. So the denominator, the numerator, the whole thing should be some kind of real numbers. So we don't have to worry about any non-real complex numbers such as 2i plus 1 or 5 minus 3i, something like that. And in this case, we know that the bottom here cannot be equal to 0, because again, if it is equal to 0, we have the left hand side is some number divided by 0, and it will be undefined, or it will actually be indeterminate if the top is also 0. So because of our setup, we know that the number on the denominator part or the whole part in the denominator is something, some real number that is non-zero. So if we square that number, it will guarantee us to get a positive value back. Therefore, if we try to multiply the denominator by the square of the denominator on both sides, we're now multiplying a positive value, meaning if we're multiplying a positive value, we do not have to worry about the change of the sign. And therefore, now we just simply have one copy left on the left hand side, and on the right hand side we just have two copies of x minus 2, which is the denominator. Good. So now we can actually try to end up solving this inequality that both sides have no denominator or fraction containing anymore. So we're now just trying to solve the inequality of polynomials. So let's try to bring the negative sign to the other side. So we actually will get 0 is greater than 2 times x minus 2 squared plus absolute value of x plus 1 times x minus 2. And now, of course, we can just, on the right hand side, we can now factor out one copy of x minus 2 to leave us the first term is 2, the coefficient, times one copy of x minus 2 that is remaining, plus the second term. As we factor out the x minus 2, we just have absolute value of x plus 1. Good. So now we can try to kind of simplify everything inside the bracket to give us 2x minus 2 times 2, which is 4, plus 1, which is minus 3. And then we have plus or minus, or a plus absolute value of x. Good. So we just have the right hand side is less than the left hand side, which is 0. And now we just need to solve this inequality. Okay, so what can we do? Well, first, this part is going to give us a certain value, which is x is equal to 2. If we try to set the inequality sign as equality, okay, just like how we usually solve inequality of polynomials in degree 2 or higher. As we factor out, we now just try to solve for the zeros and then trying to figure out the last step. Then from the first part, we will actually end up with x is 2. Well, in this step, we'll just use equal sign for a moment, by assuming that now we're doing an equation. Okay, then later on we will just trying to substitute back in and to figure out. But what happened to the second term, the second factor here? We have an absolute value of x inside. What do we need to do? In this case, we just need to split this into two different cases, like how we solve an equation of a modulus function, because we know that x could be positive and negative. Of course, it could be 0. 0 will be lying on both cases, so you can choose one or another. Meaning, for this part here, we now need to consider two cases. If x is non-negative, and if x is negative. So what would that tell us? If x is non-negative or 0 or positive, then absolute value of x would just be the same as x, since x is either 0 or positive value. So the absolute value of that number would just be itself, such as positive 3 still be positive 3 after the absolute value. 0 will still be 0 when after the absolute value. So in this case, the middle term here plus absolute value of x would just give us plus x. So that the whole thing would turn into 2x plus x, which is 3x, minus 3, the constant here. Now, if x is less than 0, meaning if x is negative, by the definition of modulus or absolute sign, we need to flip it into positive, or we need to take away the sign. So that no matter what value we choose for x in this case, it will turn out to be negative x or minus x. So we get 2x minus x, which gives us 1 copy of x left, minus 3. But what does that do? Well, here comes the problem. Because now we're saying that when we have two different cases, we need to compare with this case here. So let's try to bring it up on top and then finalize our solution. All right, so from the last board, we end up with the following results, which we need to split into two different cases by setting x is either positive or 0, or when x is less than 0, which is negative. And in each case, we actually will get the second parts in some conclusion that we actually end up with different expressions. So why does that matter? Because now we can just consider each case, and in each case, the second term has no longer contained the absolute value sign or the modulus, and instead we can just simply rewrite the expression of the second factor as just a linear factor or a linear polynomial. So in this case, we actually get either 3x minus 3 or x minus 3. So of course, for the first case, we can just simply factor out the 3 or divide by 3 because 3 is clearly not 0 and in fact it's positive. So we will actually end up with x minus 2 times x minus 1 is less than 0. And again, that is just because now when we say 0 is greater than the right hand side, we can also say that the right hand side is less than 0 by reading it backwardly. And then the sign here will also read backward, okay, from small to bigger. Good. So what does that do? Well, we know how to solve the inequality of polynomials after we factor out, especially. Then, and again, one of my old videos, we have talked about how to get the solution of inequalities of polynomials in general when we know the order of each solution or each zero, or you can call it each root of the polynomial itself. So in this case, we have the two roots, positive 1 and positive 2. So if we try to rewrite the order, we'll just get, of course, 1 is smaller than 2. So we will have the following. 1 is smaller than 2, so 1 goes first, 2 goes second. And since we want this product to be less than 0 or negative, the final results will be the x value has to lie between the two roots. Okay, good. So now we need to go back and check if it satisfies our condition when x is greater than or equal to 0. Well, this part here is already contained inside of the condition that we have. So now we actually can conclude that this is part of our solution, which is good. And of course, we're not done. We need to figure out the second case. But now if we trace back to the second case, we have here, we again can rewrite that the right hand side, x minus 2 times x minus 3 is now less than the left hand side, which is 0. And again, we're just reading it backwardly. Then using the similar arguments that we had, we have 2 and 3 as the two roots of the polynomial. So we will end up with 2 is less than x, which is less than 3, meaning that x is a line between 2 and 3. But now, as we trace back to the condition that we set up, If we combine these two together, we actually end up with no solutions. Again, when x is supposed to be lying between 2 and 3, we want x to be negative. But if x is already bigger than 2, there is no way that x can be negative at the same time. So this part will actually give us no solution. And therefore, our final answer of the inequality that we started off with is just this part. X is lying between 1 or 2. Or you can just write it as a set notation. X is in between 1 and 2, excluding the endpoints. And that's it. That will be the solution of our inequality. Okay, thank you for watching, and don't forget to like and subscribe to this video and also to my channel, so that you will be able to find out more of my other videos. And if you have any thoughts or anything that you are concerned about in this video, you can also leave your comments below. And last but not least, don't forget to turn on the notification so that whenever I have new videos upload, you will not miss it either. I'll see you guys next time.